And today I'm going to share a bit about my experience and what new people coming into security often ask me and the answers I have for them. So how I'm going to arrange today's talk is going to be like this. So first we're going to go through a few questions I often get asked, and together with each question we'll have a case study that hopefully will help to convey my point about what I think about real-world vulnerability research. And after that, we'll have time for some of the questions you guys might have. Does that sound good?
Yeah, perfect. Yeah.
Okay. I lost mine. Okay, so before we start, let me do a simple introduction about who I am. I am a CTF player at the team Balsn, which is a Taiwanese team. I've been working on machine learning and product security for the past 3 to 4 years. Yeah, I'm currently working at ArcAne and doing blockchain security. Okay, that's all I have to share about me. So let's get started. So the first question I get asked about vulnerability research is that people new to this industry often ask me that if they don't have any prior experience in doing any bug hunting in real world products, then where can they start? And is it hard to find bugs? So yeah, I guess this is a common question for many people, and I won't reveal the answer right now. So let's start with looking at a case study, and hopefully we can reach the same conclusion at the end. So the first case study we're going to look at here is the mu HTTP server, which is the default HTTP server for OpenWRT. If any of you guys are familiar with what OpenWRT is operating system commonly used in IoT devices. And so it's pretty lightweight, and it has all of those useful building blocks built into the implementation, including the HTTP server. And what's this? Never mind. Okay, and the HTTP server is responsible for handling a lot of stuff. Like you can imagine, for an IoT device, there's usually a web page interface which users can either configure their devices or, for example, if it's a surveillance camera, then they can probably access the video footage from the web interface. So to allow this to happen, we have to have an HTTP server, right? And the HTTP server also needs to handle a lot of stuff like static file serving, like API rerouting. So it can send out the request to the individual components that should handle the actual business logic of the IoT device. And sometimes for some special devices like a storage device, you will probably also have to provide the functionality of listing directories. So that's what the mu HTTP server must do. Okay, so since we're doing like API routing and like file serving, then we don't have to parse the URL provided by the user. That's a common part of most HTTP servers. So to do this, mu HTTP server kind of like has this procedure to handle the URL it receives from the user. And I won't go into the details of how it's implemented. I'll only go over the high-level description because that's enough for us to understand the bug. So first, you can imagine that when we're trying to access a web page, we won't type the entire path of the file we're accessing or the resource we're trying to access. We only type the special what's it called, the UI part, and the HTTP server is responsible for appending the doc root or whatever kind of like namespace separator that is used to prevent you from accessing resources aren't supposed to be able to access. So this is also the first step that the mu HTTP server does. And after preventing the doc root, then the next step that follows after it is trying to normalize the path. Because like if we don't normalize the path, it's easy for the user to pass in some path traversal patterns and escape the doc root. So this is the second step that the HTTP server does to the URL it receives. Okay. For those interested, here's the code that's that handles the path normalization part. And we can see that I think the most important part here is that we copy the path into the destination buffer, which is the path copy. No, we copy it into a temporary buffer, which is a path copy, and then we try to resolve it iteratively into the destination buffer, which is the path resolved. Okay, we're going to take a quick look at the code. It's not really that important, just to give you an idea of how it works. So I'll stop here for like, I guess, half a minute. And if you guys have any questions during the talk, you can just, I don't know, just ask it directly. Okay. So after the path normalization, the final step that the HTTP server, the new HTTP server does is it checks if the provided path still resides in the doc root. Because you can imagine with the path normalization, what we removed all like those parent directory patterns, we're still able to construct final passes, final directory, finally file passes that resides outside the doc root. So it's important to finally check that the resolved path still resides inside the doc root. So this is the last step. This is the step we do after normalizing the path. And after that, one final step is taken to append a slash after the path if the provided path is a directory. Okay, this is what we do here. We check the stat of the file, and if it's a directory, we append a slash. Okay, that's pretty much all the mu HTTP server does for parsing URLs. So, any questions? No? Now, having looked at the entire procedure, now let's think about what can go wrong here. Okay, if anyone has an answer, you can type it in the Google Docs, or you can just open the mic and share your thoughts. If no, I'll continue after like a minute. And if you want to look at a specific slide or a specific part of the parser, then you can also tell me, and I'll switch to that page. Path copy could overflow. Okay, let's see. So no, it couldn't overflow because like we're declaring a buffer of the pass max size here, and we're also only copying pass max size here. But that's a good point to start. Okay, any other ideas? No? Then let's continue. Okay, so let's do this by looking at an example. So imagine if we're trying to access the path like this. This is provided inside the URL as a path. And let's go through the steps which process the path normalization and see what happens. So first we'll prepend the doc root, right? So the entire path becomes something like this. And this will get copied into the source buffer. And then we start to normalize it. So normalizing process kind of like works iteratively. So we first process the first component, which is the triple W part, the doc root part. And there's no path traversal or current directory or parent directory patterns here. So we just copy it directly into the destination buffer. And at this point, our destination buffer pointer, which is the place where we write the next part of the path, is pointing here. Okay. After that, the next part we're going to process is the parent directory pattern here. And by processing this pattern, we're effectively throwing away the last part of the resolved path. So we're throwing away the triple W slash part. And this doesn't write anything new to the destination buffer. It just moves the cursor to right after the slash here, meaning that we've discarded this pattern and we're going to write the following parts starting here. Okay, that's for processing the parent directory pattern. And after that is the 4 A's and 2 dots and the slash. And this is not a pattern for directory traversal, because like this could be a normal file name. So we just copy that directly here. And following after that, the etc part is also just a normal file name or path throughout the within the for the file you want to access. So we also copy that here directly. So after processing those, we copy those into the buffer and move our cursor here. Okay, now here's the important part. So after that comes the 2 parent directory patterns. And we have to throw away the last 2 parts that is in the destination, the last 2 parts of the path, which is in the destination buffer. So we're throwing away the etc part and the 4 A's and 2 dots part. So after this, we move the cursor from here to here. And then after that comes the triple W part. So that also looks like a normal path. So we just copy the triple W here and we move our cursor here. And at the end, we null terminate our buffer because we finished parsing these and normalizing the path. So we null terminate the buffer here, okay, which leaves us with those stuff in the destination buffer. Okay, so that's all we do for normalization. And after that, we check whether the path is within the doc root, right? So this stuff slash triple W is the doc root itself. So it definitely resides within the doc root. So that will pass a check. And after that, we will finally see if the provided path is a directory and append the slash if it is. And the bug occurs here because like we're only appending the slash, but not adding a null terminator right after it. So while the original resolved path is null terminated. After we append the slash, it might connect it with the remaining, the leftover stuff in the buffer, and allow us to traverse the traverse outside of the block root with this. Okay, any questions? Can you guys understand the concept behind this bug?
No questions.
Okay, great. Okay, great. So what we see here is a simple, kind of like a memory, kind of like not checking the contents of a buffer and allowing leftover contents to affect the final results of our path normalization. And the impacts are pretty obvious. Like if the device enables listing directories and it uses mu HTTPT, then we can read any file. Also, we can list any directory outside of the doc root. And since we're talking about OpenWRT, which is using IoTs, we need to think about how this might impact the device. And the most obvious impact is that like some routers or some IP cameras, they store important information as the file names, like a UID of a user session or something like that. And by listing the directories, you can easily get access to those information. And this might be helpful in further attacking the device or whatever you're trying to do. So yeah, that's the first case study we're looking at. And actually, this bug was discovered like, I think around 2 years ago when I was reviewing a random IoT device that I laid my hands on. And after finding this bug, I became curious about if there's a bug so obvious lying in a commonly used code base, and this would be a huge problem, right? It wouldn't be just for the specific device I'm trying to examine. It would be a problem for hundreds or thousands of devices. So I went to check the official repo of OpenWRT, and it turned out the bug was fixed like 5 to 6 years ago in a code refactor. And it's probably not intentional because the patch, the commit is not tagged as a security sensitive one. It's just a random commit that refactors some of the code. So it's highly possible that many of the devices in the world didn't even know that there was a security issue in this part of the code and didn't bother to update their devices, because it's sometimes costly to distribute the patches to thousands of those low-cost devices and have them to do an app update. So IoT devices often don't do this, and they might remain vulnerable in the wild. So yeah, that's the first case study. So what I personally learned from this is that first, dependency management is hard, even if a bug is patched. If it's not applied to the device or whatever product we're talking about, then it doesn't work. You have to patch the bug and apply it for it to work. And since there are those kinds of low-cost devices all around the world, and the amount of them are kind of like increasing with time, it often doesn't make sense for user to, not that it doesn't make sense, but users often don't pay enough attention to updates for those devices, and the consequence of this is that they're often vulnerable to old security vulnerabilities, and this provides a good opportunity for people getting into security, because like you don't even have to find fancy techniques or new bugs. If you learn the product well enough and you know what technology or what code is using, chances are that all the bugs in the code are actually used for exploiting the device. And this would provide you a good opportunity to learn about how security research works in the wild, because like you get hands-on experience on the product, and you also get the thrill of actually finding a bug in something that actually matters. So now let's get back to the original question we're starting from. So is it hard to find bugs in devices, in real-world devices? Sometimes it is, but sometimes it isn't as hard as you think. And by choosing the right target, you can easily find low-hanging bugs that probably can earn you a bounty or give you some boost in your confidence that you're making progress in doing security research. So yeah, that's my answer to the first question. Okay. Any questions here? Why was the cursor moved before processing the last www? Okay, I didn't see that question. Why was the cursor moved before processing the last www? You mean here? Oh, we're processing 2 hash traversal patterns, so we need to eliminate the last 2 components that are within the resolved path. And that effectively means we're moving the cursor here, just like we're throwing those 2 parts away. Does that answer your question?
I see.
Yes.
Okay, great. So, okay, that's all for the first question. And now let's look at the second question. So the second question people often ask me is that with all kinds of new mitigations coming out every year, and with people starting to implement those mitigations and actually caring about security, will binary exploitation still survive it? Like in 5 or 10 years, what will we see in the binary exploitation landscape? Will there still be memory corruption bugs, or will they all be prevented with enough mitigations, or probably not eliminated, but made unexploitable? Okay, so this is the second question people often ask me. And since there are all kinds of mitigations and it's hard to discuss them all together, I'm going to look at a specific case of a specific type of mitigation or hardening today. So the case we're going to discuss today is that like people started writing software in Rust. Even the kernel developers for Windows started adopting Rust to write their modules. And with those supposedly safe languages, how is it possible for there to still be memory corruption bugs? Okay, and for this, we're going to look at another case study. And this part is the Solana blockchain. A bit of background knowledge around the project we're talking about. The Solana blockchain is it's a blockchain node, and it includes an component, which is a VM within it. And for the VM, since we're talking about a virtual machine that should be accessible to the public, and it's supposed to run a lot of stuff, it definitely needs some kind of optimization. And that's what Solana did with its VM. It implemented a lot of optimizations, including just-in-time compile of the bytecode and memory sharing scheme for certain resources between the between different VM runtime. Okay, we're probably not going to look at the just-in-time compilation part here because that is not relevant for the case I'm trying to share today. But we'll look at the memory sharing optimization in the following few pages. Okay, and some more background knowledge. The programs the programs that are running the Solana VM are allowed to call other programs, which is called program invocation. And this is required because, like, you can imagine the functionality of a program is kind of limited. And to allow it to do more complex stuff, we have to allow programs to interact with each other. It's somewhat similar to what we do in a normal operating system. You can have your shell call another binary to do stuff for you. That's also what happens in the small VM. What is different here is that the execution of programs are sequential, which means that if a program calls another program, then the second program must finish and return whatever results that it gets after computation to the first program before the first one can continue execution. Okay, and I guess that's enough background knowledge for what we're looking at today. So let's start looking at the actual code. So we're talking about programs within VMs and cross-program invocations, right? So if we have two programs, the first program, which invokes the second program, then they need to have two different VM instances, because like you wouldn't expect the second program to be able to modify stuff, modify the program state, modify the runtime state of the first program. So you definitely need to have two different VM instances. And yeah, did I forget to? Yeah. Oh, and I forgot to talk about this. So, so between programs, sometimes we have to share resources, like certain data from the first program to the second program. And this is done through data units called accounts, which you can treat it as just a byte stream or something like that. Yeah. So when the first program invokes the second program, and supposedly, and if it wants to pass data to the second program, it kind of like specifies the part of the data it want to share and wrap it out in an account and pass it to the second program. So this is the way memory sharing is expected to work. And you can imagine the most naive approach for doing this is just to copy the data, copy all of the data in the source account to the second VM instance and write it into the destination account. And after the second program execution ends, we take the data and write it back to the first program, because like we want to see any changes that are made in the destination, in the account. So this is a naive approach that could be taken if we were trying to do account memory. We're trying to pass data between two VM instances. Okay, hope that sounds reasonable to you guys. Okay, and the problem with the naive approach is that if the data we're passing appears to be very large, then it would be costly to copy it from the first program to the second program, and then from the second program back to the first program. And this cost is not negligible if we were talking about hundreds of megabytes of accounts passing. So what Solana tries to do here is it tries to avoid the copying, and does this through a memory sharing scheme, which is basically like mapping a part of memory on the host into the first program and into the second program, so that both programs can see the changes done on this part of the memory. Okay, this is a basic idea of the memory sharing optimization Solana is trying to do. And yeah, the pros are pretty obvious. Like you don't have to copy the data anymore, so we're eliminating 2 copies per invocation at least. But there is one special part where we need to consider when doing this kind of memory sharing, which is like if the second virtual machine, the second program, tries to increase the size of the account, it tries to grow the size of the account data, then what would happen? You definitely can't write the appended data right after the host buffer, because like we didn't pre-allocate any memory for that. So we have to allocate another buffer to accommodate the account changes, the account growth. But if we do that, then when we're returning to the first program, we also have to fix this mapping, because this buffer would be released. It would no longer be used, and the data all changes to the data will be written to the second buffer, the newly allocated buffer. So if we grow the account data size in the second program, then when we return to the first program, we will have to fix the memory mapping. Okay, any questions? This might be a bit more complex than the first case study, but it should still be understandable.
I guess I have a question, but I already found out the answer from Phineas. So the execution, you mentioned that the execution is serialized, but this is across the entire system. It's not only for each VM. So nothing can be done in parallel. Is that correct?
Yeah.
Okay. And then the second question is: there can you not impose a limit on that account such that the second VM does not increase it, beyond a certain limit? I mean.
Yeah, we certainly can do that, but there's other. Yeah, sorry.
I'm sorry. I was wondering how is the first VM? How does it get an acknowledgement that the account was increased or the size of it is increased? How does it know?
Yeah, that's what we're going to talk about in a while.
I'm jumping ahead.
But that's a good question. Whether the first VM can impose a limit to the size that can increase. Practically, yes. And actually, Solana kind of does it. It sets a limit to the max increment of data that an account can have. But it doesn't kind of like require all subsequent calls to not increase the data. This is related to how data management is done in Solana, because like we only treated account as data sharing units, but in practice, accounts are actually associated with an owner. And only if the program is the owner of the account, then can it modify the contents in the account. So in practice, cross-program invocation is often used for a program to pass an account it doesn't have ownership to the second program, which has ownership to the account, and let the second program modify the account data on behalf of the first program. And because of this design, it doesn't make sense to for the first program to kind of like require the second program to not increase the account data size, because like only the second program can do that. And if it imposes its limitations, then it will be impossible for the account to append any data. So if we're not considering this, if we're not specifically considering this usage, then it's possible to impose limits, but the design of Solana kind of like requires us to not impose the limitation. Okay. So any more questions? I guess no. Okay. So yeah, this is what we talk about. So after returning to the first program, we must update the mapping. And okay, this is probably not that important. No, this is important. Okay, so what we're looking previously is just the overall concept. In practice, a program can have access to multiple accounts, and it can also pass multiple account references to the second program. So in practice, the mapping will probably look more like this. We have several accounts mapped to several different buffers. And yeah, that's what actually happens in real programs. So so let's talk about the update part. So after returning from the second VM, and if one of the accounts are grown, then we have to have a way to decide which mapping to update, right? We have to decide whether the second account buffer belongs to the second account or to the first account. It might seem obvious from this graph that this should be mapped here, but for the VM processor to work, it must have a way to look up which account to map to the second buffer to update the mapping. And to understand how this works, we have to look at the internal structures of the mapping management. So, okay, let's see how to do. Okay, so we have to, I have to share a bit more information about how account works to introduce the concept. So for an account, there's actually more to just pure data. There's actually some metadata like the owner of the account, which we previously mentioned. And we also have the balance of account, because like in Solana, in the blockchain system, an account is usually associated with the tokens with the coins that a user should have. So it also have some metadata regarding the balance of account and probably a few other stuff. And yeah, that's aside from the account data, which is just general purpose data. So since the account contains those two components, we have to decide whether to map the entire account through direct mapping, through memory sharing, or just part of the account data through memory sharing. And if you think about it, it makes sense to only share the account data part, because like the metadata would be pretty small in size, probably just on the scale of 30 to 50 bytes. And the overhead of managing the memory mapping would be more costly than actually just copying the data wherever we need it. So the only part that we could benefit from memory sharing is the account data. So that's what Solana does. So for an account, there would be a virtual memory pointer which points to the account data that resides in the virtual memory of the program VM. And there would be a memory region structure stored on the host, which also holds a pointer to the virtual address of the account data that is stored in the virtual machine. And it also stores a host buffer, which points to the actual buffer on the host that contains the account data. So this is how the memory mapping works. Whenever we try to access some data, we look up the relevant memory region, find the matching virtual memory pointer, and translate it to the host buffer pointer, and then access data through the host buffer. Okay, does it make sense? It's probably a bit more complex. So let me know if you have any questions.
Yeah, we're fine. Please continue.
Okay. So yeah, so when we're returning from an invocation, and we have to decide whether when we're trying to do an invocation, what Solana does is it takes the virtual memory pointer and stores it in a temporary structure on the host called the caller account. And this structure is we're going to use this structure when we return from invocation. And yeah, these are probably not that important. These are the code that's responsible for taking the virtual memory pointer and storing it on the host. So I'm just going to go through it. Like here, we translate the account infos, which is the account structure in the virtual machine. We translate it and get the host address of where those stuff are stored on the host. And after we get the account infrastructure, we try to fetch the VM data address from the structure and store it in the caller account structure. The VM data address is this pointer, which is a pointer to the virtual address of the account data in the virtual machine. Okay. And yeah, these are just the utility functions. Okay. And when returning from the invocation, how Solana decides which account to update is like it takes the new caller account, which has the virtual memory pointer, and compares it with each memory region. Okay, compares with each memory region, and if it sees a match, then it means that the caller account belongs to this memory region. And then it checks whether the new data buffer matches the host buffer stored in this memory region. If it doesn't match, then it means that an update happened, and we have to modify the host buffer to point to the new account data buffer. Okay. this is how the memory mapping is updated. Okay, does it make sense? Okay, hopefully it does. Yeah, and here's the code responsible for doing that. So we check if direct mapping, the optimization is enabled, and we try to find the region. Yeah, we try to find the region responsible for the VM data address, the caller account VM data address, which kind of like where is it? Find, which calls this region function, and the find region function here, which traverses the regions to find one that contains the provided VM address. Yeah, this range. No, where is it? This range contains the VM address. Okay, so we're trying to find a memory region where the virtual memory range specified here contains the address provided by the caller account. Okay, and if it does, then we found the region and we get the host address of the region and compare it with the new buffer for the caller account. If it doesn't match, then we have to update the pointer. Okay, this is what we're doing here. And here's the code. And okay, any questions? If not, then let's start thinking about what can go wrong in this entire cross-program invocation memory sharing scheme. Okay, as usual, I give you like 1 to 2 minutes to think about what might go wrong, what seems sketchy, or whatever else you find intuitive. And after that, we'll start looking into what the bug is. Can you DOS by recursively having the program execute to spawn a new VM? Okay. Yes and no. What we talk about, the design we covered today doesn't include the DOS protection part, which is built into the VM itself. For you can imagine that for a general program, for a general Turing complete program, there's no way of predetermining whether the program will halt, which is the halting problem, right? So blockchains also have this problem. If we allow users to run arbitrary programs in blockchain, which is what blockchain programs are kind of supposed to do, then we don't have a way to determine whether the program is malicious or not, whether it's intended to cause a loss or not. So how those blockchains usually handle these kind of problems is by specifying a computation budget for each program. So basically, every operation within the program consumes part of the budget. And if you use up the entire budget, then the VM just aborts your execution and tells you that the execution fails. Okay, that's how DOS is prevented, and it's not covered in the design we're talking about today. But yeah, that's kind of like building the Solana. Okay, any thoughts on the bug? Might be, yeah, it's not as obvious as the previous one, so might be a bit hard. If no, let's look at the actual bug. Okay. So we talked about how the lookup procedure is done, right? we have to take this VM pointer and compare it with the pointer stored in each memory region. But let's think about this. This pointer is a virtual address, and the virtual address is taken from the VM itself. So what this means is that we can actually modify this virtual address to an arbitrary value and have the host take the arbitrary virtual address and store it in the caller account. So imagine we change the originally the account 1 as a data pointer, have a virtual data address pointer which points to the account 1 data that resides in the VM. Imagine if we change it to a pointer that points to the data of the second account. So what will happen is that during invocation, the host wouldn't care about what this pointer has, and it will still take the pointer and store it in the caller account. And the caller account will now incorrectly point to the data buffer of the second account within the VM. And when we return from the invocation and trying to look up the which memory region to update, we'll notice the host will notice that the data VM pointer matches the pointer of the second memory region, and we'll try to update the host buffer of the second memory region instead of the host buffer of the first memory region. Okay, so this is definitely something incorrect, right? But what impact would it have? So let's imagine that the accounts have data of different sizes, and the second account data is slightly, the size of the second account data is a lot bigger than the size of the first account data. So after we update the pointer, after we return from invocation, we'll try to update the pointer, and we'll change the host buffer pointer from the account 2 data to the new account 1 data, which might still be smaller than the account 2 data. And this would effectively map the virtual memory for account 2 data to the host heap memory region that is here. And since account 2 data is larger in size than account 1 data, this the size of this memory, the range of this memory, the length of this memory will be greater than the length of the account 1 data. And since we're only doing mapping of the start address, then if we try to write to the latter parts of the account 2 data, we'll actually get an out-of-bound write to the host heap. Okay, does this make sense?
Yes, it does. Thank you.
Okay, great. So yeah, we're talking about a program written in Rust. And so why do we still have those kinds of memory corruption bugs? The reason is, for many kinds of optimization, like just-in-time, compile, or like those memory sharing schemes, it's practically impossible to write it in safe code. So even if you're using Rust or other safe languages, to allow yourself to write optimizations, you sometimes have to resort to using unsafe blocks, or you have to get around the protection that the language provides you, or whatever the mitigation starts to prevent. And since those kinds of optimizations are often required or like critical for performance, for products that require high performance, it can be said that it's practically impossible to entirely avoid usage of unsafe blocks in some kinds of real-world products. And if we're starting to use unsafe blocks, we're basically throwing all kinds of protections that the language provides outside of the window. And with that, memory bugs can still exist. Okay. So now let's go back to the original question we have here. So we're talking about people starting to write code in supposedly more secure languages, but this movement doesn't actually eliminate all memory corruptions, because like if we're writing a kernel, it's impossible to not use unsafe code, because like if you're trying to access raw physical memory, how can you not use unsafe? And yeah, and we've seen with like performance critical products, they also have to use unsafe. So the answer here is that my answer here is that ultimately the developers will do what they want or what they need for the product to work, and that often works against the security. And even if they're starting to use more secure languages, well, it might eliminate a certain portion of the bugs. It might limit the attack surface. We can't completely. It won't completely remove all memory corruption bugs or all memory-related bugs. And yeah, that's pretty much my answer. With all those mitigations, it would kind of like make exploitation harder or make the attack surface smaller, but there will still always be memory bugs in the end. Okay, that's the second question in my answer. If there aren't any questions, I'm going to move on to the last question we're going to look at today. So the last question people ask me is that, so yeah, we're talking about using unsafe in a safe language, and everyone knows that's bad. And supposedly the developers also pay attention to the unsafe code. And if they do this properly, if they do some rough analysis of their unsafe code and make sure it is safe, then everything will be fine, right? We won't have any more memory bugs. So is this claim true? Let's look at the third case study. So the third case study is about Whitebeam, which is a random project I found on GitHub one day. And the description of the project states that it's a sandbox that is used to restrict user access to certain resources, and it's supposed to kind of like prevent a user from opening a file or calling a function, a dangerous function in a library. And yeah, that's what it's supposed to do. But yeah, that's what it's supposed to do. But the catch is that it requires that the program itself doesn't have any inherent bugs, because like it's only limiting a resource or a library function call access through a very specific way, which we'll talk about later. So it's actually more of an access hardening tool. You can imagine it as a complement to the file permission system of Linux or something like that. It's not a real sandbox in any way. Yeah, but the intention is to limit resource access. Okay, this is the third case study we're going to look at today. And so, yeah, so we need to start talking about how it actually works. So how the Whitebeam works is that it tries to use the GNU loader features to hook all library access and loads to files and stuff like that. It tries to hook stuff through the function resolving part. For those familiar with binary exploitation, it's trying to hook the PLT resolve function, if you know what I'm talking about. Like we need to use the PLT stub to jump into the loader, which will resolve the function and write it back into the GOT table. It's trying to hook this process and do some checks on the function we're calling, and yeah, if it's not reasonable, then it will block it. Okay, that's how Whitebeam works. But we won't go into the details today because like that's not the most important part to the bug. Yeah, and to summarize it in a single sentence, it's trying to sanitize all cross-boundary access, which means if you're calling a function from a binary, if you're calling a function in B library from a binary, or if you're calling a function in B library from a library, then you're trying to catch all those cross-boundary access to resources and sanitize those actions. Okay, so we're probably not going to look at much of the code here. We're just going to look at the high-level concept of how it works. So basically, it works like this. If the executable is trying to call a function in the share library, the whitebeam function will intercept this call and push the function we're calling into a function stack, which is loaded into the program as a launch of the program. Okay, it will push the function into here. And after pushing it, it will replace the function call. Because like we're hijacking the PLT redirect part, right? And by returning a different function, we can replace the function that is going to be called. So it replaces the function called to a generic hook inside the whitebeam library. And the generic, what is this? This is the pushing part. Like we hijack the PLT, we hook the PLT redirect function, and we push the hook ID, which corresponds to the library we're calling into and the function name we're calling into, as well as the redirect address we're going to use into the hook, into the function stack. So we're hooking the function and pushing it. Yeah. And then we're going to call the generic hook function here. Okay, this is basically returning the generic hook as a result function, and we're going to call it. Okay, and after we call the generic hook, let's see what happens in here. First, it pops the function from the function stack, and then it does all kinds of downstream check. Like if you're doing a file access, it might check the file name, check the user, or check a lot of other stuff. And if you're calling a function, it might also check the user and the permission you have. So this generic hook first pops the function and checks what you're trying to do, like with respect to the stuff it popped. And if you pass all checks, then it calls the resolved function. If it doesn't, it blocks the function call. Okay, that's what generic hook does. And we're not going to talk about the actual checking part because like it's pretty much just a list matching of rules against a user, and it's not relevant for the bug we're going to talk today. So I'm going to skip that part. So this is code for popping the function from the function stack. This is a generic hook function, and we're popping the function, and yeah, we're popping the function, and we're going to do a lot of other checking, like after this. Okay, any questions about this procedure? No? Okay, then let's start thinking about what can go wrong here. Like this replacing function, pushing it into a stack and popping it later. What can go wrong here? Would a fork still be hooked? Yes. Do you mean the forked process or the fork function itself? The fork function would be hooked. And as for the forked process, this depends on the configuration provided to whitebeam, but you can assume it will still be overlooked by whitebeam. So yeah, a fork process will still be hooked. Okay, a little hint for this. Think about how we're passing, but that's not the only problem. So yeah, it's entirely broken. No, we don't even have to do this. Yeah, never mind. Okay, I guess let's go on to the answer. So the problem here is that we're pushing the function calls to a global stack within the process itself. So you can imagine that if we have more than one thread, then if we don't do the push and pop atomically, then there could be a race condition. So for example, if the first thread is calling the read function in the standard library, then and we intercept the read function, and we push it into the function stack, and then it's supposed to be replaced into the generic hook function, right? But before the generic hook function execute, the second thread calls the write function, which is also intercepted and pushed into the function stack. Then after we call the generic hook from the first thread, it tries to pop from the function stack, and it actually retrieves the write function instead of the read function. And this means that we're actually swapping function here. This first thread expects to call read, and the second thread expects to call write. But due to the race condition, we're calling it, we're swapping the function calls between the two threads. Yeah, and that is a big problem. So that is not only a problem for like sandboxing itself, it's a problem for the original program. It's like, you can imagine if we swap two functions in an arbitrary, if we swap two functions across two threads for an arbitrary program, there's a high chance that the program would just crash. And if we're even more unlucky, then the swap will probably result in something that is exploitable, like we're doing the read and write swap here. If we're reading to a buffer, we write it. If we're expected to write from a buffer, but we read to it instead, then if any following code trusts the data in the buffer, then it might become exploitable. So this is what is happening here. Like the function swapping due to the race condition that makes the sandbox unsafe and makes the original program unfunctional. Yeah, okay, that's the third case study. So what we've seen here is that, like for Rust, it's impossible to detect race conditions during the compilation time. And yeah, it's generally impractical to detect race condition statically. So some kinds of language like Go, they have those race detectors, but it also only works in certain scenarios. So what we're seeing here is that, well, we have all kinds of mitigations, including like safe languages that should prevent memory correction. The best it can do is prevent directory. Okay, the best it can do is to prevent those obvious bugs, or like for us, we probably also have some additional checks on ownership to prevent you from have two references that are used incorrectly. But for certain bugs like race conditions, it's practically hard for any mitigation to fully prevent. And this will likely still exist even with a lot of current mitigations applied. Whether it will be exploitable or how hard it will be to exploit those bugs is hard to tell, but those bugs won't disappear or won't be like completely blocked by all those kinds of mitigations. Okay, yeah. So circling back to the question, yes, if developers pay attention to their code and scrutinize their unsafe blocks, then yeah, direct memory corruptions will probably be rare. But this is not a bad thing in itself, at least from my point of view, because like memory corruption has been prevalent for too long. We've been spending too much time looking at those pretty dumb bugs like buffer overflow or something like that. And with those mitigations in place, we can actually shift our attentions toward more interesting bugs like race conditions, like logic bugs in the program. So yeah, with all those protections, binary exploitation will definitely change. In that the type of bugs that are common might no longer be memory corruptions, but we'll always have all kinds of other bug classes that are not preventable or that are hard to catch that could eventually lead to memory corruptions or eventually lead to exploitable scenarios. Okay, that's my answer to these 3 questions. And yeah, I guess that's all for sharing. And now I'm going to talk about the conclusion I have from my past few years of experiencing binary exploitation. So what I believe we're seeing in recent years is a paradigm shift. Like, I think when I first started security, like 4 to 5 years ago, most of the bugs that you see are memory corruption bugs, like probably 70 to 80% or something like that. Most of the binary related bugs. But in recent years, we've seen, well, memory corruption bugs are still like the majority of the bugs. We're seeing more and more interesting bugs, like logic ones, like crazy stuff in compiler optimization or stuff like that. And yeah, I believe this is a good thing for researchers, because like those kind of bugs are more interesting, at least to me. And another good thing is I see people starting to explore like the underexplored fields, like the race condition or undefined behaviors in certain languages. Like, for example, in Rust, if you're casing between C representation of structures and casing back to Rust structures, if you're not careful with the value that is contained in the C structures, then it's easy to actually write undefined behaviors into your code, which often turns out to be exploitable. And those are stuff that people didn't pay attention to 3 to 4 years ago and are now being explored. And I see that as a good direction for vulnerability research in general. Okay, and yeah, and another thing that we can think about is that since there's a paradigm shift or the kind of bugs are changing, what can we do to adapt to this new environment? The answer for me is actually a lot. For example, we have all kinds of fuzzers, we have all kinds of like symbolic executions that are supposed to find memory corruption bugs. But for race conditions or like the undefined behavior ones, we often don't have enough tools or we don't have good tools for finding those. And this is a huge part of security that could be improved. And I'm not really sure how many people are currently working on this, but I think not a lot, which means that if you're interested in this and you're starting to work in this, you might actually invent something that is relevant for the entire security industry. And that could be very impactful. Yeah, so I believe this paradigm shift is actually providing a lot of chances and opening a lot of doors for binary related security researchers. And another thing I'm observing is like, since we're moving from those simple memory, probably not simple, but from those plain memory corruption bugs, which are pretty dumb, to be honest. Since we're moving from those kinds of bugs to more complex bug classes, it might no longer be sufficient if you only know specific skill classes. Like if you're only familiar with the heap layout of the standard library with Chrome heap layout, or like, I don't know, with how to leak the cannon on the sec. If you're only familiar with those kind of Pwning skills, it might be hard for you to survive in the security research industry in the future. So what I'm seeing is like people are starting to learn new skills to be able to survive, to be able to find new bugs in the industry. This means that security research might become more demanding in the future, but it also means that it would probably be easier for you to find unique bugs that other people won't find. It's like nobody no longer has the same set of skills, and maybe only your skill set is enough to find these specific kind of bug. And yeah, this also provides a lot of opportunities for security researchers. So yeah, my answer to the previous questions is that binary exploitation is not hard. For like in the following 5 to 10 years, we definitely have code written in C or like IoT devices that are easily exploitable. And if you're moving past this stage into the tougher targets, then you have a lot of stuff to explore, and it's an exciting opportunity. And for all those interested, I would like to like encourage you to pursue this path of career in the future. Okay, that's all for today. That's all for my sharing. Any questions?
No.
Oh, can you hear me?
Yeah, sure.
Yeah, maybe I have a question. Do you feel like with the difficulty of exploitation rising up, is the bounty of the exploits also going up?
So what the bounty of the exploit is going up or down?
Up. Do you feel like they're going up?
Well, that's a good question.
Where do you feel that the exploits market is currently at for binary exploitation?
I don't. To be honest, I don't really know, because like I feel like the opportunities are increasing. Because like when I first started, there are not that much binary exploitation bounty programs, and in recent years, there's the Google VRP program, which includes Chrome, includes the kernel, and even KVM itself, which is a lot of stuff to explore if you're interested in that. And for example, there are other products that are binary related, like the Solana blockchain, where I think most people won't think about binary exploitation when talking about blockchains, maybe more related to smart contract or stuff, because there's actually a lot of binary exploitation opportunities in this field too. So if we're talking about the amount of bounty programs, I believe it's going up. But if we're talking about like the exploitation market as in selling exploit to governments, I'm not sure about that industry. Yeah, it's probably still a big industry, but I don't feel like there's much growth in there.
You guys have any questions? Maybe I have a follow-up one to this one. So you're saying that you're seeing more exploits now. I mean, it's also true because of your skill level getting better and better. So you see more opportunities. But would you say that we write worse code, or we just write more code and there are more opportunities, or are there now just more bounty programs that encourage people to look into this? Like, what would you say about the average quality or security of the code being written nowadays compared to whenever you want? Are we doing better or worse? Like, how could you assess?
I feel like it's probably on the same level as when I started. So there's definitely more code, but that's probably just me looking at more projects now. Yeah. As for the code quality, it's probably the same. The code quality hasn't really improved at least from the projects I looked at, haven't really improved in the recent years. If you're looking at a specific product, then it probably improves. But since there's always new products coming in, then the initial code qualities for those new projects are usually poor, and it kind of like fills in the place of whatever improved. So in general, the code quality is probably not changing much. And yeah, I think bounty programs related to binary stuff is definitely increasing.
Let's hope we put that to good use and eliminate some of the worst mistakes that made that affect the people, right?
Yeah.
That's just the hope. Okay, I don't know. Do you guys have any other questions? If not, James, I want to thank you very much for this lovely talk. Your questions were not very approachable on the first glimpse like this, right? But you draw the attention to some important aspects here. Every time you share resources and you have multiple actors acting upon those resources, there's always a space to exploit some vulnerabilities. So this is very true for the memory, right, operation. And now it looks like many of these lessons that we learned in the days could be carried on to these newer projects like blockchain and so on. I'm not familiar with the Solana blockchain, but I'm sure that it could be improved as any other piece of code. So thank you again for your time, and hopefully we'll see you again. I don't know which context, but it would be great to host you again.
Thanks for inviting me today.
Yeah, you're welcome. Thank you. Have a lovely day.
Okay, see you guys.
Bye-bye.
Bye.